So this is example 2. The straight rod was example 1. And let's do both of the cases where it's either uniform or non-uniform. And we want to find the potential here at the centers. Okay? What would be the formula for that? That one is going to end up being pretty simple. Again, it's going to end up being much simpler than doing the electric field version of this. Remember, the electric field version was we had to take one piece there, one piece here, go like that, and then this one exerts electric field like that. Then we cancel their x component, only their y component. We cancel their y component, only the x component survives. Then we integrate it. This one is, again, much simpler. You just say, take a piece there, take a piece here, and then integrate over the whole rod. And the distance is equal to, the distance doesn't change, right? So uniform and non-uniform, well, what's going to happen? Since the distance is all the same, from here to here, from here to here, from here to here, from here to here, k dq over r, right? So if I integrate it over the whole rod, the integral doesn't even become an integral. It's just they all add up, right? You just add, integrate. And r is the same, so it comes out of the integral. K comes out of the integral. The integral of dq is just q. That's the answer. K dq, kq over r, since it's a uniform distance. How about if it's non-uniform charge density? Let's say there's more charge over here. Let's say it's like this. Lambda equals kx, where x is from the middle. From middle of rod. Remember, for the electric field, we did the same thing. We said, imagine if the uniform density, imagine if the charge is increasing, and you have more charge here at the end. And then we calculated the electric field. What was which electric field was stronger? Uniform rod, was the electric field here stronger versus more charge here, and the electric field here? Do you remember from chapter 23? Or even if you don't remember, think about it now. In which case should the electric field be stronger? Well, if you have more charge here and the electric field of this one is down, the electric field of this one is up, they're canceling. So, and then the electric field due to these two, the charge there is weak, and their electric field doesn't cancel as much. So the weak electric field is not canceling, the strong electric field is canceling. So I would expect the electric field here to be weaker if the charge density is increasing versus uniform charge. Okay? How about potential? If there's more charge here, do they cancel over there in the center? No, they just keep adding to each other, right? Because there's no direction involved with potential. So this one adds to this one adds to that. So really, the answer is going to be the same. It's just going to be kq over r. It's not going to matter if there's more charge here, more charge here, since the distance is all the same, the integral really doesn't matter. You see, because r is the same, it comes out, this comes out, and then dq is lambda x, right? But in other words, if I went through the formal way of doing it, lambda dx, but everything here is still constant in terms of yeah, you see, if you take the r out and you take the k out and you integrate lambda dx, well, the integral of lambda dx is q, right? It doesn't matter how the lambda changes as a function of x. The integral of lambda dx is q. So the answer still comes out to be kq over r. Would I be able to do this? Would I be able to solve for the potential at some other point here other than the exact center? Let's see here. Can we set up a certain okay, so now I'm going to take a little piece here, and I'm going to say, let's say this distance is x from the center. Let's see if it's a doable integral, or can we set it up, okay? And then here I take a little dq, and the distance is going to be what? R. Now, is the r going to be the same from here to here versus here to here? No, the r does change as a function of where you are on the rod, right? So it's not, the formula is not just going to be kq over x, right? We're going to actually have to do an integral here. You know what? Let me draw this a little bigger. Okay, well, this angle is theta, right? And this is 180 minus theta. Okay. So I'm going to have to integrate this dv is equal to k dq over r. dq is equal to lambda dx. And if it's a uniform charge density, the lambda comes out of the integral. So it'll just be k lambda integral. And then the dx is equal to what? We used this technique for the electric field. We said dx was r d theta, right? And then this one is square root of you know what? Let me not call this one x. Let me call this one d, because you might get it confused with this x, the x measured from the rod. So I'll just call that d. So k lambda r d theta, and then the r is equal to what? Well, I guess we could use the cosine, the law of cosines, right? R is equal to d squared plus r squared minus 2 times r times d times cosine of 180 minus theta, right? Which is what? Is there an easier way of writing cosine of 180 minus theta? That's equal to is there an easy way of writing that? Is that sine of theta?